This lecture is something of a bonus lecture, I guess, in a way. Last year, I added this one to the curriculum because it does have a lot of applicability to retrofit projects in existing buildings, even though this is one of the newer HVAC technologies. Well, I say newer. It's been around since I think the late 1980s is when the first VRF system came out. But it primarily stayed in Europe and I think Japan. But in the United States, in the last 10 or 15 years, we've seen a lot of VRF systems being installed, and it's becoming much more prominent around here. So tonight, this is a little bit of a shorter lecture, so hopefully you appreciate that, and the homework is a bit shorter as well. Don't all applause at once. So variable refrigerant flow. So this type of system is effectively a special type of heat pump. And this is a good place to talk about it because last week we talked all about air source heat pumps and the fundamentals of how heat pumps work. And so this is a good system to piggyback on top of that as an extension of those concepts. VRF systems typically are air source, which, as a reminder, that just means that the heat sink or the heat source is just the ambient air surrounding our building. That's where we are either rejecting our heat when we're in air conditioning mode, or that's where we are pulling our heat when we're in heating mode. But you can have a water source VRF system as well. They just tend to be less common. Today, we're going to focus on air source style systems because that's a simpler version of a heat pump, and we haven't really talked about water source heat pumps yet. Most DX processes, so any process that's a direct expansion refrigerant-based process, whether that's heating or cooling, are either an on or off type of system. It's a binary kind of system where the system is either on or it's off. So when your thermostat says, hey, we're getting warm in here, that sends a signal to your air conditioner that says, I want cooling. And when that system turns on, you just get full-blown cooling. It goes to 100% output until the space is happy, gets close to the set point of whatever temperature you want to maintain in that room. And conversely, if your thermostat calls for heating, you just get full heating again until you get to about where you want to be from a temperature perspective. And the issue here is generally you don't have the ability to provide that partial heating or cooling. And the equipment just ends up cycling on and then off and then on and off between 100% output and 0% output. The problem with this is this leads to this oscillation where, let's say you want to maintain 70 degrees in your room. Well, as your heating or your cooling kicks on and off, you're actually going to oscillate around that point. You're going to overshoot it, undershoot it, and that's just going to happen over and over again. And I'll have a visual here to help illustrate that. And these type of systems, so these are effectively constant refrigerant flow systems. They only have one speed at which they can operate. You either get all of the refrigerant capacity or you get none of it. But a variable system like VRF, it's right in the name, variable refrigerant flow, means we can vary our heating or cooling output to what that space actually wants. So let's say we had a typical on-off style cooling system. we are trying to maintain 75 degrees in our room. The actual space temperature is going to be something like that. We want 75 degrees, but we're not going to get exactly 75 degrees. And the cooling system, if we're looking at the cooling output, well, let's say our cooling system is off, and then as our temperature rises, that sends a signal to say, hey, turn our cooling on. And now we get 100% output. It maintains that 100% output for a while. And since our air conditioner is running, our temperature starts to drop. And eventually it will cross whatever temperature we're trying to maintain. And it will undershoot it a bit until it gets to the point where we say, okay, that's enough, turn it off. So the cooling system goes completely off, temperature starts to rise again, cooling system turns on, and it just keeps doing this all day long. Just on, off, and you get this decently wide swing of temperature around the point at which you want to maintain. So this could actually be going up to 76 down to 74. That wouldn't be that bad, but if you had wider swings, maybe plus or minus 2 degrees, that might not sound like a lot, but 2 degrees actually makes a pretty big difference for the just the perception and the comfort of someone in a space. Now, to contrast this, a system that has variable cooling capacity, you're going to get a much tighter band or a tighter oscillation range that's going to be much closer to where you want to be. You still don't get that perfect flat line. I mean, no system can provide that level of comfort, but the cooling output can go anywhere from 0 to 100% depending on what that space needs. And so if you have a conference room and people walk in, a big group of people for a meeting, let's say, then the cooling output will start to ramp up to a higher level. And then when everyone leaves, it'll ramp down. Or maybe throughout the day, if there's windows in that room as the sun comes around and shines in the window. But this is one good advantage of a VRF, or really any variable capacity system, which there are many. This isn't unique to VRF. This is just the first time we've talked about it. And this isn't really an energy discussion, honestly. This is more of a design consideration. Whether you're providing this variable output or this on off, from an energy perspective, it's probably going to be fairly comparable, because at the end of the day, you are still outputting on average probably about the same BTUs per hour on average throughout the day. It's just instead of turning it on and off, you get this nice variable output to match whatever the active load is. So there are 3 basic components of a VRF system. You have your indoor fan coils, and I'll talk about each of these in more depth here in a second. You have your branch selector boxes. Sometimes they're called branch controllers. There's even a third term that I'm blanking on right now. Every manufacturer has their own term for it. And then you have your outdoor heat pumps. A standard DX system, your typical air conditioner, is usually paired 1-to-1, where you have one indoor coil and you have one outdoor coil at the heat pump, which we talked about in depth last time. So it's usually a 1-to-1 pairing. You have one coil per one outdoor unit. VRF systems, though, have multiple indoor coils that all link up back to one common outdoor heat pump. So you could have 30 to 40 indoor coils that match up to one heat pump, one very large heat pump outside. And this is one big what I call a refrigerant network. And if you think back to one of the project highlights I talked about towards the beginning of this class, not today's class, but the overall class, we talked about this system. That was that school that was built 100 years ago where we put in a VRF system. And this is the basic schematic of what that looks like. So you have your heat pump outdoors. You have, in this case, 2 branch selectors or branch controllers. You could have more than that. Sometimes there's really only a need for 1. Sometimes you might need 10 of them. It just depends on the project. And then you have all of your indoor fan coils. And they make all kinds of different types of fan coils. They all have essentially the same components. There's a DX coil in here with a fan to blow air. In this case, air is sucked in through this center grill. This sits in the ceiling, so you would see this overhead. Air is sucked in through the center grill. It goes through a DX coil behind this face, and then it's either heated or cooled depending on what the space needs, and then the supply air blows out all 4 sides. This unit right here is designed to be mounted just up on the wall, so you would see this within the space. This pulls air in through the top, runs it through a DX coil, and then blows it out the bottom, either hot air or cold air. And all of this stuff is connected with refrigerant piping. And you might notice that on this side of it, I'm showing 3 pipes, and then everything down here is 2 pipe down to the fan coils. And that has to do with how this system does what's called heat recovery. I'll get more into that here in a moment. But this is the basic schematic. That branch selector box, what this does is every pair of ports, so each one of these takes up 2 pipe connection ports on here. Inside this box is a little solenoid valve that can reverse the refrigerant flow direction based on the individual thermostat calls at each one of these units. So recall last lecture, we talked about how a heat pump will reverse the refrigerant flow depending on if it's in heating mode or cooling mode. This is effectively doing the same thing, except this is on an individual level for every fan coil. We can reverse the flow through each pair of pipes, depending on what each one of these needs. So the indoor fan coils, these are the things that are going to give us our hot or our cold air into the space as determined by each individual thermostat connected into each one of those units. And all that is really in there is just a really small supply air fan and a DX refrigerant coil. And that's it. These fan coils usually recirculate air within the space. Normally they are not connected to an outside air connection point like a traditional air handling unit. So normally we have to provide ventilation air separately, and we'll get more into that down the road when we talk about heat recovery outside air systems. The branch selectors are basically a piping manifold. So all of the fan coils connected to that box, it basically is just a bunch of spaghetti coming out of that thing and going out to the fan coils. And this is the primary device that's going to change the refrigerant flow direction depending on what those fan coils want, and allows all these units to be connected into one network. And I'll explain why that's a great thing here coming up. And then we have the outdoor heat pumps. So this is the thing that's really going to provide our heating or cooling to the overall system. And it is a special type of heat pump, but fundamentally, it's operating on the exact same principles. It's either going to pull heat out of the air to deliver into our VRF system, or it's going to reject heat into the air from the VRF system, depending on what's going on. Are we in heating mode? Are we in cooling mode? These systems are extremely efficient. Main reason being is they have what's called energy recovery. So we are going to have some spaces in our building that are going to be calling for cooling. Any one of those fan coils that is in cooling mode, they are taking heat out of the space and then rejecting that heat into the refrigerant, which then goes into the overall network. And you could have some other spaces in your building that are calling for heat. So this could be, maybe it's a moderately cold day, but you have a conference room in the middle of your building that is chock full of people. That conference room is still going to need cooling, even if other spaces need heating because it is a cold day. Any of those rooms that are calling for heat, they're going to be taking heat out of the refrigerant and then delivering it into the space. Because in a VRF system, all of our fan coils are connected to one common network. What this means is that when you have these rooms and these fan coils that are in competing modes, so some in heating, some in cooling, they can actually share energy. So if you're taking heat out of one space, you can then use that heat in a different space that actually wants that heat energy. And so that's where I come up with this term of refrigerant network. All of these rooms are communicating to each other. And ultimately, this means that the heat pump outside doesn't have to work as hard because now we're sharing energy internally. We're just moving energy around the building rather than having to reject a bunch of heat outside and absorb a bunch of heat outside. And remember that in any DX based process, the compressor power, that's the thing that makes all of this work. That's the home base in our baseball analogy. That compressor is at the heat pump. So if we can make the heat pump not work as hard and not run that compressor as hard, we can save a lot of energy. Here's a basic schematic of what this might look like. So we have our outdoor heat pump. We have our 3 branch controllers. They kind of show it almost like it looks like one pipe, but imagine 3 pipes in each of these runs, and then 2 pipes out to each fan coil. And out in our system, we have, say, these 3 units. They're in cooling mode. And so those are pulling heat out of their spaces, putting it into the refrigerant. And then we have a couple units that are in heating mode. And now those units can use that heat. And then we got a number of units that they're happy where they're at. So on a fundamental level, that's why this type of system is so efficient, or at least can be very efficient. And so with our indoor fan coils, some are rejecting heat, some are absorbing heat. There is going to be at any given time some balance of the system, and there's going to be a skewedness to what's the overall system need. So the building could be mostly in a cooling mode. So most of the fan coils, or maybe even all of the fan coils, are in cooling mode, or the building could mostly be in heating mode. And our outdoor heat pump is only going to do what it needs to do to make up whatever energy balance remains. And recall that a heat pump can only operate in heating or cooling mode. It's one or the other. It can't do both. It can do heating or cooling. You can't run that compressor and get heating and cooling out of it. It just does not work that way. So let's say we're looking at some active loads in our building at a moment in time across a number of fan coil units. And let's say we add up all of the units that are running in cooling mode, and they are pulling 80,000 BTUs per hour out of their respective spaces. And then we have a number of other units in heating mode that are delivering 120,000 BTUs per hour. If we had a traditional system, a non-VRF system, where every single zone was served by its own independent system, we would have to um, we'd have to serve that 80,000 BTUs per hour on the cooling system, and additionally serve 120,000 BTUs per hour on the heating system. So ultimately, we are processing or moving 200,000 BTUs per hour of total energy. And that would be with the traditional system that isn't able to share energy between these spaces. But if we have a fancy VRF system, 120,000, getting my numbers wrong. So we're taking, shoot, hang tight. All right, sorry about that. So we have VRF, and now this 80,000 that we are pulling out of spaces to provide cooling, we can now use that in these spaces that want that heat energy. And what that leaves us with is this 40,000 BTUs per hour of a heating balance that we now have to take care of. So we went from 200,000 to 40,000. So our outdoor heat pump, we would turn that on in heating mode, because that's how we are skewed. That's the mode that our balance is telling us we need. So we turn that on in heating mode to get that 40,000 BTUs to the system. And then the other 80,000 is just shuffled around inside. So we turn on our heat pump, we take 40,000 BTUs per hour from the surrounding air, put it into the refrigerant, and now that's in the network and can be delivered. And even though the overall system balance is in heating mode, so our outdoor unit is running in heating mode, that still means that all of our indoor fan coils can still operate in cooling mode. So just because our outdoor unit is in heating mode does not lock out cooling. And so we're still able to have those competing modes where the conference room that's loaded up can get the cooling it needs, even though the rest of the system is operating in heating mode. Depending on the balance of the system, if we're in that dominant heating mode, we can figure out how much heat pump power we need if we know the COP of that device. So the BTU per hour that we need to deliver, and that's only the balance. Well, if we know the COP, then BTU per hour delivered over BTU per hour on the input side, or you could do watts over watts because COP is dimensionless. Normally, we want to solve for watts because that's how we define electrical power. But if we figure out, hey, our system is mostly in cooling mode, and if we know the EER, if we know the cooling efficiency, then we can figure out the watts input based on the known EER. and the balance of the BTU per hour that we're taking out of the system. But just keep in mind that the BTU per hour removed or delivered, so the top terms in both of these equations, that's just the overall system balance. That's not all of the BTUs in the system. That's just the balance after we've shared energy internally. To help illustrate this a little further, let's say we have a scenario where this is an oversimplification, but I think it helps illustrate what's going on. So let's say at any given point in our building, we can be heating dominant, where we have a very high heating load, where basically everything is in heating, nothing is in cooling. Or we could have somewhere in the middle, where we still have some cooling load and some heating load. Or we could have a scenario where basically everything's in cooling, nothing's in heating. Throughout the year, we could be anywhere along this line at any given time. In the summer, we're going to be closer to this side. In the winter, we're going to be closer to this side. And in the spring and fall, we're probably going to be somewhere in the middle here. So if we have independent heating and cooling systems that have to serve those loads independently, and I just threw some rough efficiencies here. So 10.5 EER for our cooling, 2.0 COP for our heating, assuming a heat pump. So our cooling power, we don't need any if we don't have any cooling load, but we need a lot of cooling power if we have a lot of cooling load. Similarly, on the heating side, and if you looked at the combined power, if we had to run those as independent systems, the combined heating and cooling power, that's very high. I mean, throughout all of these conditions, we are always having to spend a lot of energy to serve these loads if these loads are served independently. But if we had a VRF system where instead at any given point we can share energy between our zones. So if we're on the heating side, peak heating, everything is in heating mode, we still need a lot of heat power really to make that happen. So we haven't really saved much. And then on the other side, if we have this very high cooling load, we need a lot of cooling power. So on each end of this graph, we're not really saving anything as compared to this independent system, but you can see in the middle here where we're going to get a lot of that energy sharing between our heating and our cooling load. In theory, if we have this perfect balance right here, we don't need to run the heat pump at all. And so that's why this zeroes out. And you also notice the VRF in heating mode. On this side of the graph, we are only running in heating mode, even though we still have cooling, but we can do that because of the energy sharing, and vice versa on the cooling side. And so the area underneath here, or within this triangle, so that would represent some theoretical savings. So if you install a VRF system that is constantly on this side, it's in cooling all day, every single unit, or on the opposite side, you're not going to see great energy savings. But if you have a lot of time somewhere in here, you can see there's substantial savings that could be gained. And again, this is a bit of an oversimplification, assuming a constant 10.5 EER and a 2.0 COP. In reality, the efficiency would vary depending on how hot or cold it is outside. But I hope this helps show what's going on and why there can be such substantial savings with the VRF system. I mentioned early on that VRF is really good for retrofitting existing buildings. So when would it make sense to put in a new VRF system? There are a number of things that could be true. So it's going to be some combination of the following. If you have tight space constraints, VRF doesn't take a lot of space. There's less ductwork needed compared to classic HVAC system type. That's because our fan coils are in the spaces themselves, and then the ventilation air that would have to be provided separately, because it's ventilation air only, would require smaller ductwork. And so a VRF system would take less ductwork and ultimately less space. The refrigerant piping is much, much smaller as compared to a traditional chilled water and hot water system, which we haven't talked about chilled and hot water yet, but that would be more of a traditional heating and cooling system. It's a lot easier to run refrigerant piping through a building than hot and chilled water piping, just because it's so much smaller. If it gets small enough, the piping literally just comes on rolls, and you're just hand bending it. You don't even have to braze any elbows or anything like that. If you have lots of small zones, like a bank of single offices, and everyone wants their own thermostat because that's the only way to make everybody happy, VRF will provide extremely good zonal control. Those indoor units go as low as 0.5 tons, which is a very, very small unit. Extremely small. That's as small as you can really get. And so every single office in that building could get its own little half-ton indoor fan coil and their own dedicated thermostat. If your building doesn't have any cooling systems today, we see this a lot with rural schools. A lot of them were built in a time where they didn't want air conditioning, or they couldn't afford to add air conditioning, and their thought is, well, if we don't have school in the summer, we'll be okay. We'll be pretty warm, at the very beginning of the school year and the end of the school year, but we'll just deal with it. That type of mentality is going away. And now it's more common that schools want air conditioners in their building. And I'm specifically talking about Washington. If you are in a climate that is a lot warmer than Spokane, of course they're going to have cooling. But in Washington, a lot of those smaller schools in the center of the state, especially, they just deal with it. So VRF, this is a great way to provide a new heating system and a new cooling system using the same system. You install the system once and you get heating and cooling. So that's a pretty cool thing, and it's fairly cost effective. You could have a building where they don't even have natural gas, and so VRF is going to be way more efficient than electric resistance heat. And if you don't have natural gas available, really your only options are resistance heat, which is very expensive, or you could have like a diesel boiler, which is a giant pain to deal with, because normally diesel boilers they're not connected to a utility. They have a big storage tank buried underground outside, and whenever they get low on diesel, they have to call Joe's diesel store down the road, and they have to come fill it up. Additionally, VRF usually doesn't require any backup heating sources. A lot of times, we talked about this last time, a lot of times these air source heat pumps require a backup heating source for when it gets very cold and they don't run very well. VRF systems are built with more robust heat exchangers, and they get much better performance in those low outside air conditions. The same physics apply. The output and the COP does get worse as it gets colder outside, but it doesn't derate nearly as bad as a traditional heat pump system. So this is really a great system type for any rural customers who don't have natural gas service. And what if your customer says, I'm trying to get away from fossil fuels. I don't want a single fossil fuel using device at my building. So even if natural gas is an option, there are a lot of customers now who are more progressive thinking, forward thinking. They are pushing for electric sources because wind and solar is starting to rise in prominence, and we can produce electricity using renewable sources, but we can't do that with natural gas. If your building is in a moderate climate, so if you have moderate weather conditions, recall from last lecture, this is where heat pumps thrive. This is where they are most efficient. But if you have those extreme conditions, especially on the cold side, although you could have a similar problem if you have an extremely hot climate, if you get into those areas where it's 120 plus degrees Fahrenheit, you might have some issues with capacity and having it run well, but it's normally a problem in the cold climates because really it's hard to draw heat out of the air when it's minus 20 or even worse. If that's the condition you are in, then you still might need some backup heating sources potentially, or maybe VRF just is not the right move. You can also probably imagine if you're getting to minus 20 outside, you might be limited on how much of that energy sharing is going to go on. How many of your spaces in your building are actually going to be in cooling mode if it's that cold outside? You still might have a few, especially if they're internal rooms that don't have any exterior exposure. But at the end of the day, um, it might not be a good fit. So any one of these reasons, or usually it's multiple reasons, make VRF a system type that we would generally recommend. And so if you think back to when I talked about this building, this is Tico Elementary. I had a little mini lecture on it where I talked about it as kind of a project highlight for what a retrofit project might look like. But now you can look at this with a little bit different lens now that you know what's going on here. So the red boxes, those are the VRF fan coils. Those are in the ceiling, providing the heating and cooling. The yellow is our refrigerant piping network. We have our two branch selectors there, so you can see the three pipes coming into the branch box, and then you got that spaghetti of refrigerant pipe just going all over the place to hit all of these fan coils. Same thing down here, hit all of these fan coils on this side of the building. And then we have our refrigerant piping main. That's the three pipe part of it. And this is off sheet. It goes down through the floor there and then goes to the heat pumps. Let's see. I think they're sitting over here somewhere. But from the heat pumps over here, that's our main coming through. Hit that branch box, keep going, hit that branch box, and then to all the fan coils. So that's VRF. Any questions? All right. We got about a half hour. So I will stick around if anyone else wants to stick around, talk about homework or anything else. Otherwise, have a good night, and I'll talk to you Thursday.
Thanks, Professor.
Thank you.